So hi everyone, I'm Srinath, and Anna's also going to be presenting this talk. So in this talk, we'll be presenting our work on investigating the dexterity of multi-finger input. This is joint work with my supervisors, Christian Theobalt and Antti Oulasvirta. The goal of our paper is to try to So the goal of our paper is to quantify the dexterity of multi-finger input to inform the design of multi-finger mid-air gestures. We hope to convince you by the end of this talk that our method can be used for designing better mid-air gestures for your applications. I'd like to first start by showing you some examples of the amazing dexterity that the hand is capable of. As you can see here, we can make these complex gestures and we can manipulate objects skillfully using our hands. HCI researchers have always wanted to exploit the amazing dexterity of the hand to design mid-air gestural input. Although there have been several issues that have been that have prevented HCI researchers from exploiting this capacity. I'd like to explain more about what I mean by showing you an example. Imagine how nice it would be to enter text into a smartwatch just by doing gestures that look like this. In order to do this, there are several challenges that need to be overcome. First, we need to understand what the hand is doing. Therefore, like in the previous talk, we need to be able to track fine finger articulations without using any markers or other data gloves. We also need to understand more about dexterity of the hand. And in this talk, what we mean by dexterity is how fast and accurately fingers can move and how individuated they can move. Can I move my ring finger? How much can I move my ring finger without affecting my other fingers? And what are the ranges, what are the extents of the motion of each of the finger joints? And finally, once we know more about the dexterity of the hand, we can use this information to inform the design of mapping. In this text entry example, we can make use of the models that we propose here to inform the mapping between the gestures here to letters of the alphabet. In this case, in this text entry example. As we saw from the previous talk, there are in the computer vision community, there's a lot of interest in developing real-time markerless hand tracking techniques. Here are just a few examples of some of the commercially available and academic systems that are currently being used. This is just one of the challenges that I mentioned from the previous slide. There are our talk is not about the hand tracking challenge, but it is about the other two challenges that we have. Namely, how do we capture the dexterity? How do we know how to use this dexterity to inform the design of mid-air gestures? Now, you might ask the question of, do we really need to go into the trouble of understanding the dexterity, the speed and accuracy to design mid-air gestures? Can't we just use existing approaches for this? I'd like to look at some of the existing work that uses mid-air gestural input for interaction. Here's an example of the Minum keyboard, which uses the leap motion sensor to enter text using mid-air finger input. The issue with such a system is that it doesn't use all the fingers of the hand, so it's limited to using one or maybe two end effectors to interact with to enter text into the computer. Also, if you think about it, these are straightforward extensions of 2D multi-touch gestures to 3D. Applications like ShoeSense from KAI 2012 have shown us how mid-air gestures can be used in novel ways for interacting with computers. But again, the issue here is the gestures that are used there are limited to a small vocabulary gesture sets, and also there are no guarantees on performance, usability, or accuracy of these gestures. So in summary, existing approaches are not yet close to our envisioned goal of exploiting the full capacity of the human hand for interaction. Our goal, therefore, is to inform the design of high-throughput mid-air gestures so that we can use the full capacity of the human hand for interacting with computers. To do so, we need to solve two challenges that I briefly mentioned earlier. The first is understanding the dexterity, and the second is to understand how to use the dexterity that we capture to inform the design of multi-finger gestures. When we mean dexterity in this talk is three elements of dexterity: how fast and accurate fingers can move, how individuated they can move, what are the motion ranges of hands, and so on. So our approach is that we designed a single experiment that captured all these elements of dexterity that we can use to inform the design of mid-air gestures. We will also talk about how to use the models that we created to inform the design of gestures using computational gesture optimization, as well as heuristics to inform manual gesture design. I will now describe the experiment that we performed to capture these elements of dexterity. Our experiment consisted of users performing finger movements to accomplish a task. The task was a reciprocal selection task, familiar from Fitts law studies, and the goal was to reach the targets shown here in red by flexing and extending finger joints. Unlike a traditional Fitts law task, however, users had to move joint angles of the fingers as opposed to their end effector. So the targets were discrete joint angles in the joint angle space, not positions. Users were asked to do this motion as fast as possible and as accurately as possible, and the motion of the fingers was captured by a leap motion sensor. Yes. The data collected can be used to obtain a joint-specific model of speed and accuracy, of motion ranges, comfortable motion ranges, finger individuation, and these elements of dexterity. We obtained such a model for 7 joints of the hand, which is shown in this figure there. And our study had 13 participants, and in total, participants performed 45,000 aim movements. Let us now look at how we analyze this data to assess finger performance, that is, the speed and accuracy of fingers. From the Fitts selection task, we can derive an angular version of the Fitts law model to quantify performance of each joint. For each joint, we first recorded the movement range of users by asking participants to flex and extend their joint without moving other joints. We then divided this movement range into 2 to 5 bins and tested the movement performance for different bin distances. This resulted in 4 different index of difficulty conditions and 10 different selection tasks. This is how the data looks like for all trials from all participants in the case of the ring finger. As recommended in literature, we look at the effective index of difficulty of each selection task and bin the movement times into 5 groups corresponding to the previous index of difficulty range. And we used linear regression to obtain an angular version of the Fitts law model for each of the 7 joints in our experiment. We have seen how our experiment allowed us to quantify the speed and accuracy, that is the performance of each joint, the joints of the finger. Anna will now explain how we quantified finger individuation, that is how the movement of one finger affects the movement of another, and how to use this to inform the design of gestures.
Okay, let's go to the finger individuation. That is probably less known than the more familiar Fitts laws. So, as Srinath said, we track not only the endpoint of the selections, but also the full hand. So this allows us to derive the so-called Shiba Index. This was introduced in 1991 in the Journal of Neurophysiology by a guy called Mark Shiba. And he initially did some experiments with monkeys, later also with humans, to derive an index that would quantify how independently I can move a single finger from all the other fingers. And we followed his analysis that he suggests, but now in the context of mid-air interaction. So to quantify this individuation index, we need to look for so if we move a certain finger, in this example the middle finger is moved to control this cursor, and now we look at what do the other fingers do. In this example we look at the pinky finger, and you see on this plot on the right, depending on the angle of the middle finger, what is the angle that the pinky finger takes. And you see from these points that it stays rather static and is fully extended, independent of if the middle finger moves up or down. And we use linear regression again to fit a line to this, and the slope of this line then gives us a quantitative measure of how dependent the pinky finger is of the movement of the middle finger. In the example of looking at the ring finger, for example, you see that this relation is much larger, so there is a higher dependence of the ring finger on the middle finger, as you can see on yourself if you move the middle finger up or down. So we use these slopes of these fitted lines. We do that for all the other fingers that are not instructed, and take the average of that to compute the Shiba index. So this is a measure for the independence of the fingers. And so we have these results in the papers. They come in form of models, in form of tables. You can look them up, and they are ready to use for your analysis or for your design of mid-air gestures. As I said, we have joint specific models for the performance. Those are the Fitzler models. We have models for the individuation, which is the Shiba index, and we report on these movement ranges. So now we have everything for this first point, which quantifies the dexterity. And now we want to do some design. We want to use our results to inform the design of mid-air gestures. This can come in form of so we can use our results as design heuristics to directly make design decisions, or we can use them in computational gesture design. Yeah, I'm going to talk about it. Yeah. One example, for example, these Fitzler models could be used to evaluate existing gesture sets that we could take. For example, here you see the spelling alphabet for sign language. And we have modeled all these gestures that we could model with the gestures that we looked at, and used our Fitzler models to predict the performance achievable with that. And this was surprisingly close to the performance that is known for expert signers. Yeah, this is just a side note. But let's go back to the text entry example from the beginning. So we want to use these chord-like gestures where we use combinations of flexed or extended fingers to enter single letters. And I'm going to show you how we use our results to make informed decisions on what gestures to use for this. So the problem is how to map letters of the alphabet to these gestures that we can make. And this is a well-known problem in text entry research. It's an instance of the general assignment problem, which is known from combinatorial optimization. But to give you the intuition, really the problem here that we have a very large design space. So we have 27 letters, and if we just look at up or down movements of the 5 fingers, we have 32 gestures that we could assign potentially. And the number of mappings is much larger than the number of stars in the observable universe. So finding the best mapping there is a really hard task. But as I said, it's a known problem in text entry research, and we can use approaches from there to computationally optimize this mapping. And we do that by defining a usability score that we can use to rate a certain mapping. We have different aspects within the usability score with respect to performance and the anatomical constraints, the finger individuation. And for this part, we can actually directly use our data. But then we also have 2 terms on learnability and mnemonics, which comes from existing literature. And we combine these 4 parts in a linear combination, and can then use computational optimization to find the mapping that maximizes this score. And these W letters here are the weights which you could alter a bit to explore different parts of this design space and optimize mappings that are, for example, faster to use or more memorable. And we have explored different kind of mappings. We report on them in the paper here. I just want to quickly show one of the outcomes, which is called fast type, and was one of the mappings optimized for performance. The predictive performance based on Fitzler models was around 55 words per minute. And we have studied, we have done a short study to see how fast users could be in practice. So we used a word level entry paradigm where we just sampled some very frequent words, 4 to 8 character strings, and asked users to practice them for around 10 to 15 minutes to see what kind of performance could be achieved if users would practice that. And on average, they were around 22 words per minute. The best performances we saw went up to 38 words per minute. So this is not quite the performance that we predicted, and I just want to point some limitations, some challenges that we still face here. One of the more severe challenges is tracking and recognition. So there is a lot of work going on, as we have seen, and it's still not a solved problem for the hand tracking. And if the hand tracker does not recognize the gesture, or if the hand tracker fails, that severely impairs performance of the users. And users tend to perform more articulated and slower. So this is not really the high performance that we would have liked to see, and that we have seen in the videos in the beginning what the hands could do. So better tracking, but also better recognition algorithms are needed to really see the performance that we predicted. Here are some further predictions that we did based on our models, that you can get a feeling how far this mid-air text entry could be. If we would use more levels, as we have done in the study, in the Fitzler study, per finger, we could go up to 65 words per minute. If we could use 2 hands, we could go maybe up to 85 words per minute, because we can alternate between the hands and be therefore faster to prepare the gestures. To conclude, I think mid-air interaction can be highly useful in the post-touch world that we are currently entering. And new technologies, but also existing scenarios, could highly benefit of this form of input, where there is no intermediary device, where there is no touch, where we don't even have to look maybe at our fingers or at the input device. But the design of these gestures is very hard. There are a lot of possibilities there. But with our data that we have provided, I think we have a good basis to make informed decision on the design of these gestures. So we have quantified the dexterity, and we have shown in one example how you can apply that to the design of mid-air gestures. And although we have only looked at a part of this huge gesture space with these chord-like gestures, you can apply a similar methodology to look at other parts and at other classes of gestures. Thank you.
Shriming Google. I wonder if you can comment on more on the rationale of using Feit's law as a model for this type of tasks, because Feit's law is a very unidimensional abstraction of movement, and multi-finger movements are fundamentally more integrated. Alternatively, like something like Remmenhard and Norman's connectionist model might be more appropriate in here. I just wondered about your rationale of using this.
Yeah, so this is a point I didn't discuss here, but you may be wondering, we looked at single finger movements in our study and then generalized to multi-finger gestures. So this is based on the assumption that if you move several joints together, the movement would be performed in such a way that the slowest joint determines the speed of the whole movement, such that the end of the movement all the joints would come to at the same time to the end of the movement. So this is how we generalized from this. And yeah, the thing is that that the dexterity of the head, that the gesture space is so large that we had to somehow reduce this dimensionality to have a chance to even grasp some of these multi-finger gestures. And if you look at the movement of the joints independently, it is basically a 1D movement. You just move your finger up or down, and it's an angular movement. And that's why we decided to use the Fit's law for that, because we try to reach an angular target in that case.
That makes a lot of sense until you start thinking about actually how 10-finger typing are done. The reason 10-finger typing is superior in many ways is because of the high degree of parallelism. That's precisely what Fit's law doesn't model.
Yeah, that's true. That's true.